So last year in grade 11, we worked on graphing sine and cosine in degrees. And if you still have phones out or headphones, let's just set those things aside now. You can open up to, we're in the middle of lesson 3 here. So if you guys remember, our sine and cosine functions were sort of like these wave functions. They look very similar to one another. Back in grade 11, we used kind of these main quadrant separators, 0, 90, 180, 270, 360, sort of like as our key points for sine and cosine. So in the grade 11 course, we did 0, 90, 180, 270, 360. And in degrees, we can enter these in, like we can literally just enter them into our calculator. And if we were entering them in degrees in our calculator, we would have gotten out. So if I did sine 0, sine 90, sine 180, and so on, we would have gotten out 0, 1, 0, -1, and 0 for the y coordinates here. Literally just entering them into f at x equals sine x here. In grade 12, we're going to do the same thing except for in radians. So instead of 0, 90, 180, 270, 360, I'm going to have 0, pi over 2, pi, 3 pi over 2, and 2 pi. And the y coordinates are the same, right? The y coordinates don't change. We're just changing the unit of measurement for the x's. So I'll still have 0, 1, 0, -1, and 0. You can test this in your calculator as well. If you don't have to memorize it, as long as you know these 5 values. If I plug them into my calculator into sine, as long as I'm in radians, I will get these values out. Oliver?
On the test, will we always be in radian mode?
We will, yep. Okay, so we're going to graph the angle of rotation here in radians. And this will be the ratio value up here for the y's. Also, what I want to do is I want to graph all the points where the x angle of rotation will give us a y value of a half or a -1/2. So I want to graph all the halves and -1/2s as well. So I'm going to use the unit circle to help me with this, actually, to find the x's where the y's are halves and -1/2s, and I'm going to put those on my graph as well. So I just copied a picture of the unit circle. I'm using the same one as what we used up here. It's just a little bigger and clearer. So just as a reminder from our lesson from earlier this week, every point xy was equal to the point what on the unit circle? This is the first thing that we did on this lesson. xy is equal to, Lexi? Yep. Yes. And this is true anywhere on the unit circle, right? So here's what I want to know. I want to know, because we're working with the sine theta function, I want to find all the values around this unit circle that have y coordinates of halves and -1/2s. So I want you guys to look around your unit circle here. And I want you to see if you can find, look on the points, and I want to see where sine theta is going to equal a y coordinate of half and -1/2. Where does that happen? Lexi? Not pi over x. Okay. It's like pi over x, I don't know. Okay, so pi over 6 is one of them because it has a y coordinate of a half. There's others as well. Oscar? Sure, go for it.
Pi over 6, 5 pi over 6, 7 pi over 6, 5.
Great. And these are positive in the quadrants where sine will be positive and negative in the quadrants where sine is negative, right? Athena? So that's the x coordinate, though. I'm just looking for the y coordinate because we're working with the sine function, and I'm looking at the y's. But we'll use that in a second. Okay, so here's all my x's. My x's will be the angles. So we said pi over 6 was one of them. And it had a ratio of positive half because that was in the all quadrant. So I'm using this and this as my x and y. Okay, the next one was the rotation of 5 pi over 6, and that was also positive half. So we'll add that to our chart. Next one was 7 pi over 6, and that was negative half because it's in the tan quadrant. And the last one was 11 pi over 6, and that was also negative half because it's in the cosine quadrant. You can even just test the values in your calculator and see which ones for sine give you positive halves, negative halves. That's what we're looking for. So you don't even have to memorize. As long as you know the angles around the unit circle, you could literally plug all of them in for sine and get values for all of them for the sine function. Lexi? So normally we would just use these 5 main ones as our key points. We are going to need to use these later when we graph the reciprocal ratios. So that's a good question. Okay? All right, so let's graph it, guys. We'll do half and 1 and negative half and negative 1 here. And the x's are going to be labeled, I'm going to go up by 30 degrees, but in radians. So I'm going to go up by pi over 6's. And we know that pi over 6's come from all of these values, right, when we split into 6 equal slices. So I'm literally going to label all of my values with all of these values going up, except for the pi over 4's, because the pi over 4's are the 45's. So I'm going by 30's in degrees. So it will be like 30, 60, 90, 120, 150, but the radian values of those. Does that make sense? You can also do just like pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6, and so on, and just reduce them all at the end. But we have them all here for us anyways, so we'll just label here. Okay? So it goes 1 pi over 6, which is just pi over 6. 2 pi over 6 reduces to pi over 3. Actually, maybe I'll do this on the opposite side here. That was 2 pi over 6. 3 pi over 6 reduces to pi over 2. 4 pi over 6 reduces to 2 pi over 3. 5 pi over 6. 6 pi over 6 is just pi. 7 pi over 6, 8 pi over 6 reducing to 4 pi over 3, 9 pi over 6 reducing to 3 pi over 2, 10 pi over 6 reducing to 5 pi over 3, 11 pi over 6, and 12 pi over 6 that will reduce to 2 pi. I can also do this in the negative direction as well, right? All the negative ones will be the negative versions of these, exact same values, just going toward the left. Okay, let's graph our points. So we have a point at 0, 0. The next point is pi over 6, half. That's right here. Next point, pi over 2, 1. Next point, 5 pi over 6 at a half. Pi 0. Next point is 7 pi over 6 at negative 2. I'm just going in order for how they're labeled on my axis here. Next point, 3 pi over 2 at negative 1. That's this point here. Next point, 11 pi over 6 at negative half. And the last point, 2 pi at 0. So there's our graph. Oscar? Oliver? Sorry, every day.
So even though we don't have like pi and pi labeled, we just write the words up zero there?
We have 2 pi and pi labeled.
I meant like in our graph. There.
We have it here. Is that what you're asking?
Well, I don't know.
So if I have pi 0, the pi is the x coordinate, the 0 is the y coordinate, right? So that's why it's on the axis. Does that make sense? Okay, domain of these functions for sine and cosine go forever in this wave pattern. So for domain, we're just going to say all real numbers. What's the range These go between certain specific values, right? What's the bottom and top boundaries of sine and cosine functions? Lexi? -1 to 1. So we would say that our graph goes, our y's go in between -1 and 1, and also equal to those. If you're doing transformations or something like that, guys, these 5 key points are enough for transformations. I added these guys on because we're going to need them in some future graphs that we do. But for transformations, all you need is these 5. That's all I'm going to be looking for, okay? Okay, we're going to graph cosine in a very similar way here. Am I okay to scroll? Okay, let's look at cosine. So the cosine function, back in grade 11, we used the same x coordinates, 0, 90, 180, 270, 360. And if we plug these into our calculator in grade 11, when we were in degree mode, we would have gotten 0, 1, -1, 0, and 1. We also talked about yesterday how we can use the unit circle to solve these without a calculator, so you could find this without a calculator as well. And we're going to do the same thing in grade 12, except for with radians, right? So same as what we mapped out for sine. So 0, pi over 2, pi, 3 pi over 2, and 2 pi. And the ratios are all the same, right? The y's are the same. So these are going to be the 5 main key points, but for our purposes in graphing the reciprocal ratios a little later today, I want to know where the halves and negative halves are for cosine. And we're going to add those onto our graph for right now. Okay, so I'm going to use the unit circle for this, but I'll give you guys a second just to get these main key points down here. Okay, let's look at the unit circle one more time. So now I'm interested in, we're graphing the cosine function. And based on our stuff from the last unit that we talked, or last lesson that we talked about, we proved that cos theta, oh, I just erased my unit circle. That's not good. Oh. Let's do this. Okay. We're back. All right, so based on our info from our previous lesson, we proved that every point on the unit circle has cos theta equal to the x coordinate on the unit circle. So now I want to know, where are all the coordinates on the unit circle? Where do they fall? Where the x coordinate is a half or a negative half? Lucas?
Pi over 3.
So one of them happens at pi over 3. We have a half there. What else?
2 pi over 3.
Another one happens here. Yep.
4 pi over 3. And then 5 pi.
Great. So did you guys notice that all the sine ones were the pi over 6 ones and all the cosine ones were the pi over 3 ones? Okay, so that's all you really need to know, is that all the halves and negative halves for sine will happen at all the pi over 6 ones, and all the halves and negative halves of cosine will happen at the pi over 3 ones. And then you use the cast rule to decide which ones are positive and negative where. Or you can just use the fact that I know the x coordinates are all negative here, so these ones must be negative. I know the x coordinates are all positive here, so these ones are positive, right? However you want to think about it. Okay, so let's add these points to our graphs here. We're going to use the angles as our x coordinates, and the halves and negative halves will be our new y coordinates for the value of the ratio at that particular angle. All right, so we're going to have the pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3, yes, thank you. And these were positive half, negative half, negative half, positive half. Same units of measurement as before. We're going to label exactly the same. So this is going to be our angle in radians. This will be the ratio value when we plug in that particular angle. For cosine, I'm going to make this 1.5 and -1 and -1/2. And then same labels on the x-axis here. We're going to go up by pi over 6s. So just going around that unit circle. Okay, so same as what we did for sine. I'm counting up by pi over 6s and then just reducing them all as I label here, just like we would label our circle. Okay, and then you can start plotting all the points that you have here. So we have the point 0, 1. Pi over 3 was a positive half. Pi over 2 was 0. 2 pi over 3, negative half. Pi was -1. 4 pi over 3, negative half. 3 pi over 2, 0. 5 pi over 3, half. And 2 pi, positive 1. It should kind of look like it makes sense, right? If I've done it correctly, it should go in a nice smooth curve there, right? Okay, I also want you guys to just going to draw your attention to how I've drawn my ends here. Sometimes people draw the ends of cosine as if it's continuing to go up, but cosine starts and ends on maximums. So it actually curves down from there. So just be mindful that it's going to curve down to the next mountain and valley from there, right? So you should be drawing your ends curving downward. Okay, sine and cosine are such similar functions. They have exactly the same domain and range as well. They're just shifted versions of one another. So x is all real numbers. It keeps going forever in both directions. And then the range is the same. The y's fall between and equal to -1 and 1. Okay, we can see that here. Do you guys recognize these graphs from last year? They should look somewhat familiar. We did lots of graphing with these. We did transformations with them, all that fun stuff. Okay, the one graph that we didn't graph last year was tan. And I know it's almost break time. We got 2 minutes here, so we'll start up on tan here. So tan is equal to, so last class we proved that tan of theta equals y over x. And we also know that on the unit circle, y equals sine theta, and x equals cos theta. So tan is also equal to, not only is it equal to y over x, it's also equal to sine theta over cos theta. This is actually a trig identity. Do you guys remember this from last year? Tan equals sine over cos? Yeah. So we're going to use that to help us with our graph. We can do it other ways as well. We can use our calculators to help with our graphing stuff if we wanted to. We can use, if we have the two values of sine and cosine for the functions here, we can use that as well to help us. So I'm gonna label out these key points here for tan, same as what we did for sine and cosine. So I'm interested in the 0, pi over 2, pi, 3 pi over 2, and 2 pi points. And in order to fill these out, I'm just going to do, for the y-coordinate, I'll take the y-coordinate of sine, and I'll put it over the y-coordinate of cosine. Another option is I can use the unit circle for this. It will just be y over x at those locations. It will be the same thing as what you do for the key points of sine and cosine. Or we can even use our calculators and just plug into our calculators to do this. So we'll do that after we come back from break, okay? I'll see you guys back at 10:15. So we're going to look at sine and cosine for these special angle values. And we're going to do sine value over cos value. So at 0, sine is 0, and cos is 1. So for tan, it will be 0 over 1 at that point. Okay, so tan 0 over 1, that gives us 0. Okay? And then for pi over 2, I'm going to look at the sine value of pi over 2, the cos value of pi over 2, do the sine value over the cos value. So we're going to have sine of pi over 2 is 1. Cos of pi over 2 is 0. So tan will be 1 over 0 at that point. What's anything over 0? Okay, so undefined, let's put a u there. Okay, same thing for pi, so I'm going to look at the y value where sine is equal to pi, the cos value where sine is equal to pi, and do the sine value over the cos value. So sine of pi, 0. Cos of pi, -1. So we're going to have 0 over -1, and that gives us 0. Okay, and then same thing again, so for 3 pi over 2, sine is -1. Cos is 0, so we'll have -1 over 0, and -1 over 0 is also undefined. I'm just going to do this one in black. And then for our last one, 2 pi, we're going to do 0 over 1. And that should give us 0. All right, the undefined values. These are locations of vertical asymptotes. So we actually have vertical asymptotes at both these locations here. Unfortunately, having a bunch of zeros and vertical asymptotes is not ideal. So I think we probably need some extra points, right? So I'm going to do a couple little extra points for tan. And we could literally do, like, if we wanted to, we could do all the pi over 6s, all the pi over 3s. You can literally just enter them into your calculator if you want to. Yep. Yeah, go ahead. The nice extra points for tan are actually the areas where tan is equal to +1 and -1, and that will give us a really good spread of points that we can use to create the graph of tan. So let's look at the unit circle for a second. Remembering as well that tan is y over x. So if I want to use the unit circle to help me with this, let's just erase what we have here. All right, so our unit circle, if the points around the unit circle are x's and y's, and tan is y over x, tan will have -1s and +1s anywhere where the points have the same x and y coordinate. Where are the points around the unit circle that have the same x and y coordinates? Where do those happen? Athena? They happen here, 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 and here. Right? All of them are √2/2, maybe positive and negative versions of those, but they happen at all the pi over 4 values. And that's what we're going to use to help us with our graph of tan. This one, so remember with the cast rule, what we're going to end up with here, tan will be positive. I'll have positive 1 here, positive 1 here, negative 1 here, because we do a positive divided by a negative, and a negative 1 here, because again, we do a negative divided by a positive. All right, so those are the 4 values that we're going to use for our graph of tan. So let's just draw those out in our table of values here. It will be pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. And when I do y over x, I do root 2 over 2 over root 2 over 2, and I just get 1 from that. So tan of pi over 4 is 1. 3 pi over 4 is in the sine quadrant, so I should get negative 1 for this one. 5 pi over 4, tan quadrant, I should get positive 1. And 7 pi over 4 is in the cosine quadrant, I'll get negative 1 for this. You can test them on your calculator too, right? As long as you're in radian mode. If I plug all these into my calculator, I can find all the positive ones and negative ones. My calculator can help with that too. I'm just reinforcing the idea of how we can use the unit circle and how it's useful, okay? All right, so same labels as before. We're going to do, this will be our angle in radians. This will be the ratio value up here. And I'm going to do 0.5 and 1, negative 0.5 and negative 1. Excuse me. And then same labels as before. So pi over 6, pi over 3, all those same ones. So let's, yeah, Oscar?
Are we ever gonna have like different values that x is 30?
You can use them consistently if you had like, if we do transformations, let's say, and you have a bunch of pi over 12s, you could label them as pi over 12s if you wanted to. For the base ones, yeah, for sure. Okay, so let's just graph, let's start with these. I'm going to graph all these points here with the vertical asymptotes. So we have a point at 0, 0. We have a vertical asymptote at pi over 2. We've got a point at pi 0. And then another vertical asymptote at 3 pi over 2. And then another 0 at 2 pi. Then we have these extra positive 1 and negative 1 points here. And these are going to happen at all the pi over 4s. We didn't label pi over 4s, though. The pi over 4s happen right in between all the pi over 3 and pi over 6s. If you look at the unit circle, notice that all these pi over 4s are happening directly in between all the pi over 3 and pi over 6 values. So we can easily just tick those off on our graph in between the pi over 3s and pi over 6s. Let's look. So one of them is going to happen in between this pi over 6 and pi over 3. One of them will happen in between this pi over 6 and pi over 3. Same thing here. Here's another one. Between the pi over 6 and pi over 3. Just label off those extra ticks there. Those will be our pi over 4, 3 pi over 4, all those. So if you wanted to, you can even add them in here as labels. I don't have a ton of room, so I'm just going to leave them as little ticks. But be aware that they are, I ticked them off as these values, okay? All right, so at pi over 4, I'm going to have a positive 1. That happens right here. At 3 pi over 4, which is this guy, I'm going to have a negative 1. At 5 pi over 4, which is this next guy, we're going to have a positive 1. And then at the last one, 7 pi over 4, we have another negative 1 here. All right, so there's one section of this graph that gives us a fuller picture of what this actually looks like, which is this section right here, because we have the vertical asymptotes that border it, and then there's 3 points in between. It sort of looks like a cubic almost, little cubics that sort of come in here and curve around the asymptotes. And this actually happens infinitely. So if I were to just sort of extend this, there should be another point up here. And actually, there'll be a vertical asymptote right along here, even though we didn't label it. I'm just sort of extending a little bit here. So there'll be another one over on this side. And then if we were to sort of extend maybe the other half of this into this direction here, we would have one down here at -1. And over here at -π/2, we would have another vertical asymptote as well. So here's our other little section here. Okay, kind of a different graph than sine and cosine, right? So the domain here is kind of interesting because the domain, this will continue infinitely to the left and right, but we have all these undefined areas that are happening in between here. And these are happening at -1π/2, π/2, so -1π/2, 1π/2, 3π/2, this is 5π/2. Another one will happen at 7π/2, 9π/2, and so on. What is the connection here? What do all of those things that I just mentioned have in common? Oliver?
An odd number of pi/2.
Odd numbers of π/2, perfect. So we're going to say for our domain, x can be anything except x is undefined, so x cannot equal odd multiples of π/2. So we're going to say k π/2, where k is a whole number, so we want to say from the set of integers, and k is odd. Okay, so this is set of integer values. Okay, and we must say that because if k were a decimal, then obviously this would not be true, right? So we want to say k is a whole number. That's what the set of integers is. And we know it's also a whole odd number. All right. Are there any restrictions on the y's? Bottom boundaries, top boundaries? No, it just goes down forever and up forever. So for the range, that one's nice and easy. We'll just say y is from the set of all real numbers. All right.